Dear students, I continue my topic on wave optics. I am explaining today about theory of interference. I am explaining coherent sources, principle of superposition. What is interference? I am explaining here the concept of interference, types of interference, relation between path difference and phase difference, and condition for maximum and minimum intensity. So all these points are explained in this video, and particularly condition for maximum and minimum intensity is a very important concept as far as exam point of view is concerned. Now let us move to coherent sources. If you take two sources of light and they are called as coherent sources of light when they emit same wavelength, same frequency, and they must be in phase. Even if they are not in phase, if they are maintaining some constant phase difference, even those pair of sources, light sources, will be called as coherent sources. Only criteria is either they should be in phase or they must have a constant phase difference. And practically it is very difficult to produce a pair of coherent sources. If you take this simple diagram, I am explaining a very simple concept wherein I can produce coherent sources of light by one single light source. This is a light source, yellow colored light source. It is falling on its first cardboard, which is having a small pinhole, and the light is coming out from this small pinhole. Now it is falling on the second cardboard, which is having two small pinholes separated by a small distance. When the light is coming out from the second cardboard through these two small pinholes, they behave like a coherent sources of light because these light waves are having a same wavelength and frequency because they derived from single light source. But you can produce a pair of coherent sources by taking two independent light sources, but practically it is very difficult. So I am showing here how to visualize in phase and out of phase concept. So I am showing two simple waves. They are falling on one another. So these two pairs of light waves, they are in phase because they are starting from same point. If you look at this second diagram, they are not starting from the same point. On the y-axis, they are starting from different points, but they are maintaining, if you observe very carefully, they are maintaining a constant phase difference. In such case also, a pair of sources will be called as coherent sources of light. But very interesting point is to understand the concept of phase and out of phase, and also the superposition principle. So you must recall what you have learned in PUC first year science about simple harmonic motion. So if you recall all the concepts of simple harmonic motion, definitely it will help you to understand the theory of interference. Now let's move to that particular slide where I am going to explain simple harmonic motion. So here I am showing one small video wherein I am going to explain how this circular motion is going to set a simple harmonic motion. You can observe here this particle is now moving on the circumference of the circle, and this circumference of the circle is called as a reference circle, and which is having a radius a, and I call this particle as a reference particle. When this particle is having its projection or its shadow is when it is falling on x dash line, I call this projection or shadow as n. Now you can observe here the shadow is falling on x dash, and when this particle is moved from x to y, its shadow or projection moves from x to o. When it moves from y to x dash, its projection moves from o to x dash. I call this o as mean position. When it moves from x dash to x, its projection moving from x dash to x crossing its mean position. You can observe here when this particle is moving continuously in a circular path, its projection is moving from x to x dash, by crossing its mean position O. So it is going to now behaving like a simple harmonic motion. You know, simple harmonic motion is nothing but a to-fro motion with respect to mean position, and acceleration is always directed towards the center. In circular motion, acceleration is always directed towards the center, and you can observe here this projection is going to set a simple harmonic motion because this projection of the particle is moving on x-axis from x to x dash. It is making to and fro motion with respect to its mean position. So I am making a simple labeling for this diagram. Here P is a particle and its projection is n is falling on x dash reference line, and the projection has a displacement. I am taking the displacement from this point O, reference point O. So the total displacement of this projection n from the center of the circle O is small x. Don't confuse here. X dash is a line. I am indicating x dash in capital letter, whereas this small x is a, so n is a projection of the particle P. So it is having a displacement x on x dash. So when this a particle is moving from x to P with a constant angular speed omega, and if it is taking t seconds to move from x to P, so displacement, angular displacement theta can be easily calculated by multiplying omega and t. In linear motion, linear displacement is equal to speed multiplied by time. In the same way, this angular displacement in a circular motion is also equals to angular speed multiplied by time. So theta equal to omega t. So theta is a angular displacement, and you can easily find out the displacement On. This On is the displacement of the projection n of this particle P on x dash. You can easily find out by applying the simple trigonometry. So On P, if you take this small triangle, ON is a adjacent side, OP is a hypotenuse side. So cos theta can be easily calculated by applying the trigonometry. Cos theta equal to adjacent side upon hypotenuse side, x upon a, and you know theta equal to omega t. Then the displacement x is equal to a into cos theta. So this is how we represent simple harmonic motion in this format, x equal to a cos omega t. So it's a function of cos. In the same way, we can represent this simple harmonic motion by sine function also. If you are taking its projection on y-axis, instead of x-axis, if you are taking the projection of this particle P, n, if you take it on y-axis, you can represent the displacement y as a sine theta. It's a function of sine. And I will show you one small animation here how this moment of so displacement x or y can be a function of cos or sine. It can be visualized using this simple animation. You can observe here, as this particle, black colored particle, is moving in a circular path, its displacement y on the y-axis, it is going to set simple harmonic motion because it is making to and fro motion with respect to its mean position. And if you plot the displacement versus time graph, then you will be having a sine curve like this. So simultaneously I am showing as this particle is moving along the circular path, so you can easily plot the displacement versus time graph continuously or simultaneously. So you can visualize very easily how a simple harmonic motion can be visualized as a function of sine or cosine. So here I am taking the displacement along the y-axis. Now coming to this second point, principle of superposition. Superposition means two states of wave at one particular time. Suppose if two or more waves they are meeting at one particular point, so definitely they will be having their own state. So there will be an effect when they meet at one particular point. So this is called superposition. Y1 and Y2 are taken as the displacement of two waves, and when they meet at one particular point, so they will be having their own state, so there will be an effect, so that effect is called superposition. So according to the principle of superposition, so if y1 and y2 are the displacement produced by two different waves, when they meet or when they superimpose at one particular point, so according to this, so y1 can be expressed as a function of sine, or you can express it as a function of cos also. So I can express this displacement produced by the first wave as a1 sine omega t, where a1 is called amplitude of the first wave. Similarly, y2 is a displacement produced by the second wave, and this is a simple function a2 sine omega t plus phi. Here I have not taken phi, and here I have taken or added one extra term phi, because I have taken initial phase. So phi is called initial phase. So there is a difference. There is a difference between these two waves. When they are having a different state, when they meet at particular point, so what is the effect that we are studying? So because of that reason only, I have taken one more extra term called initial phase. And whereas A2 is its amplitude. And if they meet at one particular point, there will be a resultant wave. So that resultant wave will be having a displacement y, capital Y, I call it as a capital Y, equal to y1 plus y2, which means whenever two waves which is having a displacement y1 and y2, when they superimpose at one particular point, the resultant displacement is equal to the addition of the displacement produced by individual wave. So this is what the principle of superposition theorem says. I will explain with the help of a diagram. Here I have taken one wave, I call it as a wave 1 blue colored, and one more wave which is in black colored, I call it as a wave 2. So they are meeting at one particular point, they are superimposing on one another. So in this case, there is a resultant amplitude or resultant wave will be produced because of the superposition of these two waves. But let us find the amplitude of the wave 2, which is a larger amplitude, and this wave 1 will be having a smaller amplitude, and I call this y1 as a displacement produced by wave 1. y2 is the displacement produced by wave 2. Displacement is nothing but a maximum amplitude. Maximum displacement can be called as amplitude. Here y1 and y2 are nothing but the maximum displacement. This maximum displacement also called as amplitude of the wave. So when these two waves they superimpose on one another like this, so there will be a resultant wave. So this resultant wave will be having a larger amplitude, because the displacement or maximum displacement or amplitude which is equal to y1 plus y2 according to the superposition principle. If first wave is having a displacement 4 in it, second wave if it is having a displacement 6 in it, the resultant wave will be having a displacement which is equal to the addition of the two displacement produced by wave 1 and wave 2. It is nothing but 10 in it. And here the displacements are added in this particular example. If I take one more example, here these two waves are in phase. Because of this state, because they are in phase, the displacement produced by individual wave has been added, and you got the resultant wave, and which is having a maximum displacement or larger displacement compared to the two individual wave. But if you take the second example here, this is a one wave, I call it as a wave 1 blue colored, and which is having a displacement in the opposite direction, and another wave which is superimposing like this. So this is a crust and this is a trough. So crust of one wave is falling on trough of another wave. In this case, this wave 2 will be having its amplitude which is indicated by red color, and when they superimpose like this, so according to the superposition principle, displacement of resultant wave is equal to the addition of the displacement of individual wave. But the thing is, one displacement is in upward direction, another displacement is in downward direction. We take this displacement produced in the downward direction as a negative, and what happens here, the positive displacement and negative displacement get cancel each other and giving resultant wave which is having a zero displacement. It is because the state of these two waves are like this is the y1 is the displacement produced by first wave, y2 is the displacement produced by the another wave. The state of these two waves are out of phase. Here in the first example they are in phase, in the second example they are out of phase. Since they are in out of phase, so the two displacements they are opposite in direction. I mean one is downward direction, another one is upward direction. So one is plus, another one is negative, they get cancel each other and giving rise zero displacement. So this is what the superposition principle is says, and these are the two best examples. So now we move on to the concept of interference. So interference is the phenomena of superposition of two or more waves having the same frequency emitted by coherent sources such that the intensity of resultant wave is get modified. So I am going to show you one diagram of a typical interference where I have taken two sources S1 and S2, and both S1 and S2 are emitting the light waves and they are propagating in one particular direction. So I am showing a thick line as a peak or crest, and trough is indicated by dashed lines. So what happens here, whenever you take two independent light sources instead of coherent sources, if you take S1 and S2 are two independent light sources, then if you put the screen here, on this screen you get only illumination. Suppose if you switch on the light source S1, you get some illumination on the screen. Then if you switch on the another source S2, then the illumination is get increased, nothing will happen. But if you take S1 and S2 as a coherent sources means the light wave emitting from S1 and S2 are having same wavelength, frequency, and they are maintaining constant phase difference. So if this is the condition, then if you maintaining a proper distance between S1 and S2, and if you have a appropriate distance between a screen and this pair of sources, then you will have a pattern like this. At one point you are getting bright intensity, at another point you are getting zero intensity. So at the center of the screen you will be having a brighter intensity, and they are surrounded by alternate dark and bright bands. So these type of bands are called interference pattern. Instead of just illumination, you are having a pattern like this. This is called interference. And we can explain the interference phenomena by simple concept like a superposition of two waves. So to understand the superposition of two waves, I am indicating a wave. This portion of wave is a trough and this portion of wave is crest. So I am indicating crest by thick line, and trough is indicated by dashed line. Here in this diagram I am showing a crest by indicated by thick line, and trough is indicated by dashed lines. So at this point intensity is zero. I call it as a node displacement. So at this point intensity of the light is maximum, so I call it as antinode. So what happens if crest of one wave, crest of S1 wave, which is falling on the crest of another wave from S2 like this. Suppose a red colored wave is a crest, now it is falling on another crest. So in this case the intensity of the light will increase. Here also I am showing the same diagram but in the form of circle. So this thick line is indicating crest, and this thick line is indicating crest of the wave from S2. So this is a crest of wave emitted by S1. This one is a crest of wave emitted by S2. Both are intersecting at this point. So here you are getting bright intensity. So this the center of the screen is bright because crest of one wave is falling on crest of another wave. Here also dashed line is falling on another dashed line. So trough is falling on the trough of another wave. Here also you are getting maximum intensity. But if you observe this diagram properly, uh, one crust one crust is now intersecting the trough of another wave here. At this point you are getting zero intensity. Suppose if this is a one wave and this is a trough and this is a crust, if superposition is like this, crust is falling on trough of another wave. So this is a crust and it is falling on another trough. So this type of superposition is called destructive one, and I'm going to explain it in the next slide. So if interference is like this, or if superposition of two waves is like this, then you get zero intensity. You can observe here, this is a crust indicated by thick line and this is a trough indicated by dashed line. So both are intersecting at this point. Here you are getting dark region or zero intensity. So this phenomena is called as interference because light is not just distributed, light is get modified, light is redistributed. At one point light energy is maximum. At the bright region the light energy is maximum. At dark region the light energy is zero. In this way the alternate dark and bright indicating the light is redistributed, and this redistribution of light, this modification in the light is because of the superposition of two waves from coherent sources, and this phenomena is called as interference. Now we go to the types of interference. There are two types of interference. One is constructive interference, another one is destructive interference. Constructive interference, which is going to result maximum intensity, and whenever destructive interference take place, then you get zero intensity or dark band. For example, if this is one wave, in case of constructive interference, what happens? Crust is falling on the crust of another wave. This type of superposition of two waves is known as constructive interference, where the displacement of resultant wave will increase. The intensity at this point is maximum, where you are getting a bright region. Then another type of interference here is one wave. This is a crust and this is a trough. So if another wave is superimposing like this, a crust is falling on trough of another wave. So the displacement produced by one wave is cancelled by the displacement produced by another wave. So you get zero intensity. So whenever the two waves are superimposing like this, when displacement produced by one wave is cancelled by, nullified by another wave, then it leads to destructive interference. Here you are getting zero intensity. In this way there are two types of interferences. Then I am going to show you one animation where I am going to explain with the help of animation about constructive interference and destructive interference. Let us start with the constructive interference. I am taking two light sources, S1 and S2, and here I am going to take one point P, and this is a wave 1 which is emitted by S1, which is going to propagate towards the point P. In the same way, wave 2 is emitted by S2 is also propagating towards the same point P. The wave from S2 will reach the point P earlier than the wave from S1. But S1 ಇಂದ ಹೊರಟಂತ ವೇವ್ ಏನಿದೆಯಲ್ಲ ಅದು P P ಅನ್ನ ಒಂದು ಸೈಕಲ್ ನಷ್ಟು ತಡವಾಗಿ ಅದು ತಲುಪುತ್ತದೆ. You can observe here. So by the time this S2 wave reaches the point P, so S1 wave is exactly away from this point P by one cycle. The difference is one cycle. So when they meet at this point P, so crust is falling on the crust of another wave. So this is called constructive interference. Due to this, you get a maximum intensity at point P. Now let us move to animation of destructive interference. I am showing again S1 source from which wave 1 is propagating, and S2 source from which wave 2 is propagating. They are moving towards the point P. So when I switch on the light sources S1 and S2 simultaneously, here the S2 source, when it reaches the point P, so S1 source is away from the point P by half cycle. ಅಂದ್ರೆ S1 ಮತ್ತೆ S2 ನಡುವೆ ಅಂತರ ಎಷ್ಟಪ್ಪ ಅಂದ್ರೆ ಅರ್ಧ ಸೈಕಲ್ ನಷ್ಟು ಅಂತರ ಇರುತ್ತದೆ. ಅಂದ್ರೆ S1 ಇಂದ ಹೊರಟಂತ ಏನು ವೇವ್ ಇದೆಯಲ್ಲ ಅದು P ಅನ್ನ ತಲುಪುತ್ತದೆ, ಬಟ್ ಅರ್ಧ ಸೈಕಲ್ ತಡವಾಗಿ ತಲುಪುತ್ತದೆ. So this is you have to observe. When I switch on the light source here, S1 S2 start already reach the point P, but by that time S1 is away from the point B by half cycle. But due to this, crust is falling on the turf of another wave. So displacement produced by one wave is nullified by or cancelled by the displacement produced by another wave. Due to this, you get zero intensity at point P. This is called a destructive interference. Now we move on to another important concept called the relationship between phase angle and path difference. Here I am showing one circle, and on the circumference of the circle at two different positions I have taken two particles. One is blue colored particle, another one is red colored particle. When the red colored particle is now moving along the circumference of the particle and makes one complete revolution, then it is going to make a 360-degree phase angle. When you plot the displacement of this particle versus time, then you get a sine wave like this. Here, if I take one complete cycle, it is 360-degree. Then if you take a half cycle, it will be 180-degree. Then if you take the 1/4 of cycle, it will be a 90-degree. Here one more particle, blue colored particle, if it is moving on the circumference of the circle and makes one complete revolution, it is also going to cover a 360-degree phase angle. And if you plot the displacement of this particle versus time, then you get a sine curve like this. So this is how we relate path difference and phase difference. Here I am going to establish a relation between path difference and phase difference. So if I take two waves, y1 is the displacement of one wave, which is indicated by a sine omega t, where a is a amplitude and omega t is a phase. And here y2 is another displacement produced by second wave, and a is its amplitude and phi is initial phase difference. And phi is initial phase for y2, and phi is a phase difference if you compare the displacement of y2 with y1. Then omega is a angular frequency and time is t is time in seconds. So I am showing the same diagram which I have shown in the previous slide, and I have indicated each part of the cycle by a phase from 0 to pi by 2, from pi by 2 pi, then it is 3 pi by 2, then it is 2 pi. So as I told in the earlier slide that a path difference lambda is nothing but a phase difference of 360 degree or 2 pi. But if I take any unknown value of path difference, then you must be able to find out the phase difference equivalent to that unknown value of path difference. You must have a formula so that whatever value of lambda I am going to substitute, I must get appropriate and equivalent phase difference. For example, if I take lambda, then what is the phase difference? It is 2 pi. If I take lambda by 2, the phase difference will be only pi. So in this way, I must have a one formula, generalized formula, so that I can convert path difference into phase difference or phase difference into path difference. So I must connect a relationship between path difference and phase difference using this formula. So phase difference phi equal to delta x into 2 pi upon lambda, or phase difference phi equal to path difference multiplied by 2 pi upon lambda. Using this simple formula, we can convert phase difference into path difference or path difference into phase difference. So to work out this, you should able to write these two sentences so that you can easily convert these two sentences into a formula. For path difference lambda, phase difference is 2 pi. For any value of path difference or for unknown value of path difference delta x, what is the value of phase difference? Cross multiplication. Then you get phase difference phi equal to path difference into 2 pi upon lambda. Suppose if I take lambda as a path difference, so what is the phase difference? I should get 2 pi is using this formula. You can cross check here. If I put path difference lambda here, lambda and lambda get cancelled, leaving only 2 pi, and that 2 pi is nothing but phase difference. This is how to calculate. This is how you have to convert phase difference into path difference or path difference into phase difference. This is called important relationship between phase difference and path difference. And these are the two important formula I am going to mention here, and these two formulas are very important to understand the theory of interference. Suppose if I take two waves, they are superimposing, and one wave is having an amplitude a1, another wave is having an amplitude a2. Then after superimposition, after intersection of two waves, so there will be a resultant wave, and that resultant wave will be having certain amplitude capital A, and it should be calculated, resultant amplitude it should be calculated using this formula, root of a1 square plus a2 square plus 2a1 a2 into cos phi, where cos phi is a phase angle, phase difference. Suppose if the phase difference is 90 degree, then cos 90 becomes 0. This term is get eliminated. So when this term get eliminated, then you get equation called a equal to root of a1 square plus a2 square. So this is a resultant amplitude. Then if I take important relationship I is equal to ka square, which indicating intensity of light is always directly proportional to the square of amplitude. So if I take intensity I1 as first wave, I2 is the intensity of second wave, A1 and A2 are the amplitude of first and second wave respectively, then I can write I1 equal to Ka1 square and I2 is equal to Ka2 square using this relationship. And there is one more formula like this for calculating the resultant intensity. I is equal to I1 plus I2 plus 2 root of I1. Very important thing is, don't put this 2 inside the root. You have to keep 2 outside the root. So 2 root I1 I2 into cos phi. So what happens if I1 and I2 are the intensity of two waves, but if the intensity of two waves, if it is same, that is both waves are having a intensity I0, in that case, and if the phase difference is 0, in that case cos 0 becomes 1. Then This equation we can write like this: I is equal to I naught. In place of I1 and I2 we have to put I naught, because we have assumed that the two waves are having a same intensity. If they are having a different intensity, then we can put I1 and I2. I1 is the intensity of first wave, I2 is the intensity of second wave. In place of I1 and I2, if you put I naught, then you get I naught plus 2 root of I naught square into cos phi. If the phase difference is 0, in phase means there is no phase difference. In such case, there is a constructive interference take place. So what is the intensity of resultant wave? You can calculate using this simple formula. I is equal to I naught plus 2 I naught into 1. 1 because cos 0 is 1. Then you get to 4 I naught. What is this 4 I naught? 4 I naught is the intensity of resultant wave. Intensity of resultant wave for constructive interference is 4 times the intensity of individual wave. You should remember this important statement. And here third term, 2 root I1 I2 cos phi. This term 2 root of I1 I2 cos phi is called interference term. So when this term is 0, there will be no interference. It is simply addition of two light. It is just like your switch on two independent light source. If you switch on the first light source, the screen is get illuminated, and if you switch on the second light source, the screen is get more illumination. The brightness will increase. Nothing will happen. If this term is becomes 0, then interference is not taking place. If this term is having certain value, then interference is taking place. So these are the two important formulas you should remember. Resultant amplitude A equal to A1 square plus A2 square plus 2A1 A2 into cos phi, and resultant intensity I is equal to I1 plus I2 plus 2 root I1 I2 into cos phi, and intensity of wave is directly proportional to the square of. We will study now the condition for maximum and minimum intensity in three different cases. In the first case, we assume that in the two waves they don't have any phase difference, and in the second case they will have a phase difference, but the phase difference is integral multiple of wavelength, and in case 3 the phase difference or path difference is a fraction part of a wavelength. So in this way we are studying about the condition for maximum and minimum intensity in three different cases. Let's start from the first case where S1 and S2 are the two sources of light, and they are emitting the light waves and they are moving towards the point P. Let us assume that Y1 is the displacement of the first wave A cos omega t, and Y2 is A cos omega t. So both are the displacement produced by S1 and S2. Then according to the superposition principle, the resultant displacement at point P is equals to the sum of the displacement produced by individual wave. So that is resultant displacement Y equal to Y1 plus Y2. If you add A cos omega t, then you get 2 cos omega t. So the resultant displacement has been increased. So it indicates that at a point P there is a constructive interference, and at point P you are getting a maximum intensity. So you have to find out what is the amount of intensity using this formula. We have studied this formula in the earlier slide. So I equal to I1 plus I2 plus 2 root I1 I2 into cos phi. So in place of I1 you have to substitute I naught. We have to assume that the intensity of both light is equals to I naught. In such case, the total intensity of the resultant wave is equals to 4 I naught. That is 4 times the individual intensity. Then this is a condition for the maximum intensity. Constructive interference is taking place, and you are having a maximum intensity which is equals to 4 I naught. So this is a case 1. So we conclude that whenever two waves they are having a zero phase difference or zero path difference. When they intersect or when they superimpose at one particular point, so at that point you will be having a maximum intensity because of constructive interference. Now let us move to case 2. Here there is a path difference, but that path difference is an integral multiple of lambda. Lambda is nothing but the wavelength of one wave, light wave. Here I have taken two sources, S1 and S2. They are propagating, the waves emitted by S1 and S2, they are propagating towards the point Q now. You can observe from this diagram the distance S1Q is smaller than the distance S2Q. So here the light wave emitted by S1, it is going to reach the point Q in 7 cycles, whereas the light wave emitted by S2, it is going to reach Q in 9 cycles. So it's not a hard and fast rule that you should take always 7 and 9 as given in your textbook. So you can take any value, but the difference between these two wave, the path difference must be equals to an integral multiple. You should not be have any fractional value of wavelength. It should be integral multiple of lambda, like 1 lambda, 2 lambda, 3 lambda, 4 lambda, or any integral multiple. The wave emitted by S1, it is going to reach Q in 7 cycles. That is why I have taken 7 lambda. And wave emitted by S2, now it is going to reach the point Q in 9 cycles. So that is why I have taken 9 lambda. The difference between these two is 2 lambda. So this 2 lambda is nothing but path difference. S2Q minus S1Q is equals to 2 lambda. So in such case, we have to again go with the same steps that we have already studied. Let us start with the displacement produced by first wave, y1 equal to a cos omega t, y2 is equal to a cos omega t minus 4 pi. So omega t is a phase, and here I have to mention what is the difference between these two waves. The difference between these two waves is 2 lambda. But 2 lambda is a path difference. So you cannot put this value here because this is a phase angle. We have to express this 2 lambda in terms of phase angle using the relationship between path difference and phase difference that we already studied. So if the wavelength is lambda, then equivalent phase difference is 360 degree or 2 pi. If the path difference is 2 lambda, then equivalent phase difference should be 4 pi. That is why I have taken 4 pi, and I have taken negative sign because the wave emitted by S2, it is going to reach Q later than the wave emitted by S1 by 2 cycles. So that is why I have taken negative sign. So 4 pi is nothing but 2 lambda, or 2 lambda is nothing but 4 pi. So both are same. So according to the principle of superposition, the resultant displacement, as usual, it is addition of the displacement produced by individual wave. So here I have to take a cos omega t for y1, a cos of omega t minus 4 pi for y2. So the total or net resultant displacement is equal to the sum of these two. But here cos of omega t minus 4 pi, according to the trigonometry, the cos of omega t minus 4 pi is equal to cos omega t. You can cross check by applying the trigonometry. If you add both, then you get again 2a cos omega t. So 2a cos omega t, which is clearly indicating that the displacement of resultant wave has been increased. So it increases only when there is a constructive interference at point P. So since both waves are meeting at point Q, and where the constructive interference is taking place, because of that reason the displacement has been increased. So because of this reason only you get a maximum intensity at point Q. So we conclude that whenever there is a path difference is equals to an integral multiple of lambda, like 1 lambda, 2 lambda, 3 lambda, 4 lambda. If difference is like this, and these two waves, when they intersect or when they superimpose at one particular point, so there will be a constructive interference. and you get a maximum intensity. As usual, maximum intensity is always equals to 4 times the intensity of individual wave. So this is a case 2. Now let us move to case 3. Just you have to remember, in the case 1 we have assumed that the path difference or phase difference was 0. Here in this case we have taken path difference or phase path difference is equal to an integral multiple of lambda. Now let us move to the case 3. In this case 3, we have taken a third point R where a wave emitted by S1 and S2, they are propagating towards it, and we have taken the wave emitted by S1, it is going to reach R in 9.75 cycles, whereas the wave emitted by S2, it is reaching the point R in 7.25 lambda. I have taken fraction because ultimately we are now verifying what will happen if the path difference is a fraction of this wavelength lambda. So here the difference between these two is 2.5 lambda. So not necessarily if you take 9.75 and 7.25 only, you can take any value, but the difference should be a fraction like 0.5, 1.5, 2.5, 3.5, 4.5 like that. So the difference should be. Now let's start the displacement produced by y1 is equal to a cos omega t, whereas y2 is the displacement produced by the second wave is a cos of omega t plus 5 pi. So plus 5 pi because the path difference between these two waves is 2.5 lambda. So for 1 lambda it is 2 pi, for 2 lambda it is 4 pi, and for 2.5 lambda it is 5 pi. And I have taken plus here omega t plus 5. If you take this second source S2 which is near to R, as this near to R, the wave emitted by S2 it is going to reach R earlier than the wave emitted by S1 by 2.5 cycles. So because of this reason, since it is reaching the point R early, so I have taken 5 pi. So 5 pi is equivalent to 2.5 lambda, or 2.5 lambda is equivalent to 5 pi. 5 pi is a phase difference, 2.5 is a lambda is a path difference. Then the resultant wave y equal to y1 plus y2, and y1 value is a cos omega t, whereas the y2 value is a cos of omega t minus 4 pi. So therefore the total resultant displacement is equal to a cos omega t, because if you consider this value cos of omega t minus 4 pi, cos of omega t plus 5 pi is equals to minus a cos omega t. If you can verify this by applying the trigonometry. So cos of omega t plus 5 pi is always equals to minus a cos omega t. This total resultant displacement becomes equals to 0, and this will clearly tells us that these two waves, they are intersecting at point R destructively. That is the reason we are having a 0 intensity at point R. So we conclude that whenever the path difference between the two waves is not equal to an integral multiple of wavelength, if the path difference is a fractional part of wavelength, then there will be a destructive interference. Destructive interference because a crest of one wave is falls on top of another wave. So displacement of one wave will be cancelled by displacement of another wave, where you are getting 0 intensity because of destructive interference. So these are the three important cases. In the first case 0. Then the summary is very important. Suppose if you have a two sources S1 and S2 coherent sources, and they are emitting the light waves, and if at one particular point P, if they are in phase, then if the path difference is equals to an integral multiple of lambda, and where n can take value 0, 1, 2, 3. If you put 0 here, path difference becomes 0. If you put n value as 1, then path difference becomes equals to lambda. If you put 2, then path difference equal to 2 lambda, and so on. So if the path difference is in this way, if the path difference is an integral multiple of wavelength, then there will be a constructive interference and the resultant intensity is always maximum, that is equals to 4I0. Now if the path difference is a fractional part of wavelength, which can be expressed in this form, n plus half into lambda. So I am taking in between values. So here I am taking 0, then you get a constructive interference. If I take 1, then you get a constructive interference. If you take between these two values 0 and 1, the between value is half. And if you take between 1 and 2, it is 1.5. Between 2 and 3, the value you get is 2.5. So like that, if you have a path difference like lambda by 2, 3 lambda by 2, 5 lambda by 2, 7 lambda by 2, like that, then there is a destructive interference and resultant intensity is always minimum or 0. So this is a summary, very important, because many times the question is asked on this concept. So write the condition for maximum and minimum intensity. So you have to write like this: whenever path difference between the two waves is equal to n lambda, an integral multiple of wavelength, then there is a constructive interference where n can take value 0, 1, 2, 3. And if the path difference is equals to a fractional part of wavelength, then there will be a destructive interference and resultant intensity is always 0. So lambda value can take 0, 1, 2, 3 and so on. So this completes the theory of interference. And now we move on to an arbitrary point, and for any value of phase difference, we will write the condition for maximum and minimum intensity. In earlier case, we were very specific. We have taken 0 path difference, then we have taken a path difference which is equals to an integral multiple of lambda. Then we have taken a path difference when it is equals to a fractional part of lambda. So in those cases, we have studied whether we are getting maximum or minimum intensity. So in this case, we take any value of phase difference or path difference. So let G is an arbitrary point or random point at which waves are intersecting and producing interference. So let us start with the displacement produced by S1, which is Y1 equal to A cos omega t, and the displacement produced by S2 is Y2 equal to A cos omega t plus phi, where phi is a phase difference, and the resultant displacement according to the principle of superposition, y equal to y1 plus y2, then it is equal to A cos omega t plus A cos omega t plus phi. But here we have to apply the trigonometrical formula so that we get a proper value of displacement. It look like cos A plus cos B. If I remove this A as a common term outside the bracket, then it will be like cos A plus cos B. Just you have to apply this simple formula: cos A plus cos B equal to 2 cos A plus B upon 2 into cos A minus B upon 2. Then you can write like this. Either you can take this cos omega t plus phi as a term and cos omega t as a B term. It is more beneficial. Then it will be like this: 2 cos. I am writing this expression in using this trigonometric formula: 2 cos omega t plus phi by 2. Here I have taken A plus B divided by 2. Omega t plus phi A and omega t, if it is treated as B. Omega t plus phi plus omega t. It will be 2 omega t plus phi divided by 2. So 2 omega t divided by 2 is nothing but omega 2. Then phi divided by 2 as it is. So it will be like a 2 cos omega t plus phi by 2 and cos phi by 2. Cos phi by 2 because I am taking A minus B. Omega t plus phi minus omega t. So omega t get cancelled, leaving only phi by 2. Then I am rearranging this last term as I am just taking out this 2 outside the bracket, 2a cos phi by 2 into cos omega t plus phi by 2, just rearrangement of this equation. Then if you observe this equation, it will be like a cos omega t plus phi. Even though it is omega t plus divided by 2, just simply treat it as a cos omega t plus phi. Here in this red colored term, it is like an amplitude term. So I can write this 2a cos phi by 2 as an amplitude of this resultant wave, because y is the displacement of the resultant wave. So 2a cos phi by 2, it will be like an amplitude. So then squaring the amplitude, because intensity is directly proportional to the square of the amplitude, while squaring this, we have to keep this cos square phi by 2 as a separate term, cos square into phi by 2, and multiplying with 4 I naught. As you know, the intensity of resultant wave, whenever two waves are intersecting, when you get a maximum intensity, the intensity of the maximum or resultant wave is always equals to 4 times the individual wave. But here is I am just multiplying this extra term cos square phi by 2, because it's also part of an amplitude. So 4 I naught into cos square phi by 2. So this is an intensity of resultant wave. So this is a very important expression you should remember, but based on this only we are going to have a conditions for maximum and minimum intensity in the second slide. Here let's start with a phase difference. If it is equals to 0 plus or minus 2 pi u plus or minus 4 pi u, so 0 means path difference 0, 2 pi u phase difference is equivalent to plus or minus lambda, plus or minus 4 pi u is equal to plus or minus 2 lambda. So if these are the value of phase difference or path difference, then you will be having a constructive interference. Then you will have a constructive interference which results to maximum intensity. On the other hand, if the phase difference is if I take between values 0 to 2 pi and 2 pi to 4 pi, if I take between values plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, corresponding to path difference plus or minus lambda by 2, plus or minus 3 lambda by 2, then we will have a destructive interference which results 0 intensity. You can see this diagram. Central bright region is indicated by a peak of one curve for phase difference theta equal to 0. Then for the phase difference here 0 afterwards, then you will have a plus or minus pi value, because immediately after the central bright region you will have a dark region on the both side. Then immediately after the dark region you will have a alternate bright and dark region. So this portion is indicating bright region, this portion is indicating dark region, and you are getting these two dark regions for the phase difference plus or minus pi. So this is a plus pi on right side, minus pi on left side. Immediately after this dark region you will have a bright region for the value of 2 pi, this one second term. Then after this term you will have a one more bright region on the left side. This is a plus 2 pi. You will have a bright region on right side. For minus 2 pi you will be having a bright region on left side. Immediately afterwards then you will have a plus or minus 3 pi. So for plus 3 pi you will be having a 0 intensity dark region on right side. For minus 3 pi you will be having 0 intensity or dark region on the left side. In this way, this central bright region is surrounded by alternate dark and bright regions for the value of 0, pi, 2 pi u, 3 pi u, 4 pi u on the right side, then minus pi u, minus 2 pi u, minus 3 pi u and minus 4 pi u on the left side. In this way we can have a condition for maximum intensity and minimum intensity for any arbitrary value.